Hello, class. This lesson is a continuation of a sequence dealing with solution stoichiometry. In our last lesson, we discussed acid and base reactions, and now we are going to do an application of both the dilution equation and acid-base reactions. Here we're going to look at neutralization calculations in exercise 11. For this, we need the formula that looks very similar to the dilution equation. MAVA equals MBVB. Now, before we can jump into this calculation, I'd like to talk about the units for a minute. The units for molarity is moles per liter. When you multiply a volume in liters by that, liters cancels and you are left with moles. So the moles of, if we say moles of acid and liters of acid here, then when we multiply, we are left with just moles of acid. We are setting this equal to a similar equation that will get us moles of base. We know we can get moles of base by multiplying the liters of base by the molarity of the base, because when we multiply those, liters of base will cancel. So what we're essentially saying in a neutralization reaction is that this statement is always true. Moles of A or moles of acid is equal to moles of B or moles of base. So in a neutralization reaction, we have essentially set equal the moles of acid to the moles of base. Now this is also going to be equal to the moles of salt as discussed in our previous lesson, because acid and base specifically refers to H plus and OH minus, and when those combine, we make water. So it makes sense that these are equal amounts. We also know that the cation that is part of the base and the anion that is part of the acid will come together to form our salt. So we will also have equal moles of salt at that point in time. Okay, let's jump into the calculations. What volume of a 0.100 molar HCl solution is needed to neutralize 25.0 mLs of 0.350 molar NaOH? So first I have to identify which is my acid and which is my base. The acid is the one with an H at the front of the formula. The base is the one with OH in the formula. Unless, of course, that base is ammonia, NH3, which is one we just have to memorize. That one is still a base, even though it does not have OH in the formula. So I'm given the molarity of acid, the volume of base, and the molarity of base. In this question, I have to solve for the volume of acid. Oops. That's better. So let's plug in, and then we can rearrange and solve. So 0.100 molar of my HCl times the volume of my acid is equal to 0.350 molar times 25.0 ml. Now, something I should say, even though before we were talking about moles and liters being needed to cancel, it is okay if you plug milliliters into your equation, because milliliters is the same as liters, just different by a factor of 1,000. So if I plug in milliliters into my dilution equation, I should expect another volume that is also in milliliters. If I have two different volumes, one in liters and one in milliliters, then I need to do a conversion and make sure that they are in consistent units. All right, so to solve for the volume of acid, I need to divide both sides by 0.100 molar. This cancels, and I'm left with VA is equal to the top 0.350 times 25 milliliters due to order of operations divided by 0.100. So 0.350 molar times 25 is 8.75 divided by 0.100. This means the volume of acid needed to neutralize that concentration of base is 87.5 milliliters. All of my given values here have three significant figures, so my answer of 87.5 is sufficient because it keeps three significant figures. All right, let's try the next one. The next one is tricky because there are actually 2 moles of OH minus for every 1 mole of calcium hydroxide. So I have to change some things to make sure that everything stays balanced. So I'm given my molarity of my base. I'm given my volume and molarity of my acid. Now, again, there are 2 moles of OH minus for every 1 mole of CaOH2. So what that means is when I plug this into the dilution equation, I need to double my molarity before I plug it in order to make sure I have the total amount of OH when I am neutralizing. So when I plug in 0.0500 molar for my acid times 35.00 milliliters, and then for my molarity, 2 moles of OH minus over 1 mole of CaOH2 times 0.0200 molar of CaOH2 times VB, my volume of base. By doing it this way, remember that molar is the same as moles per liter. So 0.200 moles over 1 liter. I will check to see that moles of calcium hydroxide cancels, and I'm left in moles per liter of OH, which is what I want to neutralize. And I know it's going to neutralize because on this side, I have moles of H plus because I've got 1 mole of H for every mole of HNO3. So let's combine like terms and then solve. I have 0.0500 times 35.0 milliliters. I'm going to divide that by 2 times my original molarity for my hydroxide. I end up needing 43.75 mLs for my base. Now, I had 4 significant figures for my volume here, but the other 2 values only had 3 significant figures. So I need to round this to 43.8 milliliters of base needed to neutralize the molarity of acid. Let's move on to the next one. Here, in a certain experiment, 28.0 milliliters of 2.50 molar HNO3 and 53.0 milliliters of 0.320 molar KOH are mixed. Calculate the number of moles of water formed in the resulting reaction. What is the concentration of H plus or OH minus ions in excess after this reaction goes to completion? All right, so this one we need a full balanced equation. I know in a neutralization reaction I will form water, and then my salt is KNO3. And we've done a problem very similar to this before, and we need to specifically look at the moles of, or first the dissociation, and then the moles of each component. So I need to find moles of H plus and moles of OH minus before I start doing the rest of my calculations. Now, if I think about the net here, I also know that this is H plus NO3 minus plus K plus and OH minus, and that forms water, and then K plus and NO3. For talking spectators, NO3 and K plus are going to go away, and I'm left with H plus and OH minus gives me water. That essentially is my net equation, but I can tie my molarity of HNO3 to H plus because it's a 1-to-1 ratio. You have 1 mole of H plus for every 1 mole of HNO3. I can also do the same thing with KOH. I have 1 mole of OH for every 1 mole of KOH. So the molarity of KOH can be used to find moles of OH. So let's set that up. I've got H plus and OH minus, and that forms H2O. And we're going to set this up kind of like a BCA table like we did before. So I need to figure out how many moles of each component I have. So I'm going to split my table here. So 28.0 mLs over 1,000 milliliters. In this particular example, we need to put it in liters first, times my molarity of HNO3. All right. So 28.0 divided by 1,000 times 0.250, and that is 0.007 moles of HNO3, which is equal to the moles of H plus, and I'm going to put that down as my before. I'm going to do the same thing with my KOH. And this is going to kind of turn into a limiting reactant question of sorts, just like we did in our last lesson. 53 divided by 1,000 times 0.320. All right, and I get 0.01696. 0.01696 moles. And since it's a 1-to-1 molar ratio, like I said here, you can just say that's the same as moles of OH minus. 0, 1, oops. Okay. Now, I can see that the moles of H is much smaller than the moles of OH, so that will be my limiting reactant. So I'm going to go ahead and subtract that amount, 0.007, to find my remainder, 0.00996 moles remaining. So here's my change. I have no H plus remaining, 0 moles of H plus, and then same change. And when I subtract that, 0.00996. of OH minus, and I had no water to begin with, at least in terms of moles I was trying to calculate. But I have that many moles added. And it looks like we're doing 3 significant figures here. So this question is asking, calculate the number of moles of water formed in the resulting reaction, and then what is the concentration of H plus or OH minus ions in excess after the reaction goes to completion. Okay, so I have figured out my number of moles of water. Now with sig figs, I should tack on 2 zeros to that. So 0.00700 moles of water. Now, careful, this is asking for a concentration. I have the number of excess moles, but I need to figure out the concentration of excess OH minus, which means I need to divide these moles by the new volume of my solution. So my volume here, since I added 28 milliliters and 53 milliliters together, I'm going to add those volumes to figure out my new total volume. 28 plus 53 is 81 milliliters, which when we divide by 1,000 is 0.081 liters. So I need to divide by 0.081 liters to get my concentration of hydroxide ions. 0.00996 divided by 0.081, and I get a concentration, if we're doing 3 significant figures, 0.123 molar OH minus left in solution. Molar OH minus. So I have 2 answers to this question. I have 0.0123 molar OH minus in excess, and then in terms of moles, 0.00700 molar, or not molar, moles of H2O. You probably should put this in scientific notation. So if you did 7.00 times 10 to the negative third moles, that would be sufficient as well. Okay. That was a taste of neutralization reactions, but also throwing some stoichiometry in there. Go ahead and try it, set 11. Okay. Keeping an eye on time, I just want to discuss acid-base titrations to wrap up this video. And then in our next sequence, we will do some calculations with our titrations. So we're basically providing some framing and application of neutralization reactions when we're talking about a titration. A titration is an experimental lab technique in which we essentially neutralize a sample of unknown acid or base, and the goal of this is to determine the concentration of that unknown acid or base. So what we're going to use is volumetric analysis, which is a technique for determining the amount of a certain substance by doing a titration. The vocabulary here is really important. We have a titrant. This is the substance that is being delivered from a burette, and it has an accurate volume and therefore also an accurate molarity. The analyte is at the bottom of the flask. That's the substance being analyzed. You are adding titrant to the analyte. Its mass or volume must be accurately known. We have the equivalence point, which is the moles of OH minus, and that is equal to the moles of H plus or H3O plus. Now that is true for an acid-base titration. There are also redox titrations, which we'll talk about what redox means in a later lesson. We have indicators. These are small, typically organic molecules that change color in response to certain pHs. and as a result, they're used to tell us when we've reached the endpoint of a titration. Phenolphthalein is one of the common ones. It turns from clear to pink around a pH of 8, which is very close to the endpoint of a strong acid, strong base titration. And then standardization is a procedure for establishing the exact concentration of a reagent, typically done through titration. Here are some very good diagrams here of what a titration looks like. So as we've discussed previously with glassware, we always measure the volume of a liquid by looking at the bottom of a meniscus. The blue burette liquid here on the left is your titrant, and the pink liquid at the bottom is the analyte. Typically, the analyte has an unknown molarity, but you know the volume and molarity of what's in your burette, and so you use that and the dilution equation to determine the concentration of your substance below. This particular flask, it says it contains vinegar and indicator. Vinegar is normally clear, but it has been neutralized and reached the endpoint at this time, so the indicator has turned from clear to pink. When you are adding titrant to your analyte, you may see a slight response in color change with the indicator, but it's temporary and it will fade quickly. This means that during the process, you are neutralizing a small amount of your analyte, but you need to continue adding base until you have completely neutralized your acid. When it is completely neutralized, the pink color will persist, and you're looking for a light pink color. If it is a very dark pink, you've gone too far and you have missed your endpoint of your titration. We will discuss a little bit more about titration analysis again in the next lesson when we pick up with exercise 12. Have a good day.